So thank you all for coming out to support Xue Jun Cheng on her completion seminar talk as part of the Complex Human Data Hub seminar series. I'd like to start by acknowledging that this talk or the seminar is taking place on the traditional lands of the Wurundjeri people of the Kulin Nation and acknowledge their elders past and present. June, I'll pass it over to you to start your talk. June is giving this talk from the luxury of her home due to some unfortunateness, which we will not mention.
Oh,
thanks, June.
Thank you, Dan. I was actually going to mention it. Hi, everyone. Thanks for coming along to my completion seminar today. It was meant to be in person. But yes, COVID, that's the mention. But I'll begin. So what I've focused on in my PhD is investigating the concept of holistic processing, primarily using a suite of tools called systems factorial technology. And I'll explore this topic further later on, but first I just wanted to set the scene. So I wanted to take you on a walk down this street. So as we go through our days, we come across and process a lot of different information. For example, when you walk down the street, you see buildings, you see cars, dogs, and the faces of people walking towards you. And of course, you don't just see these objects. We extract features and information from them, encode them into memory, categorize them, make decisions about them, all in a relatively automatic fashion. But are there differences between how we process these various types of stimuli? So in the literature, faces in particular are seen to be a special type of stimulus, and there are a couple of findings that suggest this. The first of which is called the Thatcher effect here. So you can see in this example that it was found that we don't recognize distorted features as easily in inverted faces compared to upright faces here. And another study by Yin in 1969 showed that recognition performance, whether the item had been shown before, was better for upright compared to inverted faces, but that this difference in recognition was not found for other objects such as houses and airplanes. So when stimuli were viewed upright, faces were the easiest to recognize compared to houses, airplanes, and so on. But when inverted, faces were also the most difficult to recognize compared to the other stimuli. So they called that the inversion effect. There's some caveats here though, because this inversion effect, where inversion affects faces more than non-faces, also seems to depend on expertise. So recognition performance has also been shown to be better for whole faces compared to isolated parts of faces. For example, Tanaka and Farah found that recognition of isolated parts increased within the context of the whole face compared to isolated parts by themselves and parts within a scrambled face here. So these previous studies on face processing suggest that knowing that recognition is better for upright and intact faces means that faces are processed differently. However, as mentioned earlier, there are also important implications for this idea of expertise, especially of face expertise, and the part it plays in this discussion. So all of this kind of leads to the question of whether there's actually something special about how we process faces that is stimulus specific, not tied to expertise, and if so, how might we be able to measure this? So to investigate this question, I'll be primarily talking about two methods, the composite face task and double factorial tasks. And each of these methods are applied to two stimulus sets, morphed faces and schematic faces. And lastly, I'll also be addressing two questions that arise from these studies, namely, why do the two methods show different results, and whether we can confirm the processing model that's revealed by the double factorial task. So one paradigm that has been used extensively in the phase processing literature is the composite phase paradigm. And in this paradigm, participants are asked to attend to one half of the phase, which is the target half. So for example, here they might be asked to attend to the top, and then they're shown a study phase, a mask, and then a test phase. And they're finally asked to indicate if the target half has remained the same or is different. In the partial design of this composite phase task, the target test phase half in white is either the same as or different to the corresponding study phase half, but the irrelevant half in gray is always different. So you can see that in both blue rectangles here, the target half can be the same or different, but the gray half is always different. And performance on these trials with aligned phases where the halves are together are compared to the same trials with misaligned phases of misaligned halves, and holistic processing is inferred from what they call the alignment effect, where accuracy is higher on misaligned compared to aligned trials, because you're better able to ignore the irrelevant half when the parts are misaligned. And one issue with the partial design here is that predictions in this task can only be made about same trials. So when aligned, the different irrelevant parts should affect performance on same trials because they can't be ignored. However, it's more difficult to make predictions about the different trials because the different bottom halves could either increase perceived difference between A and C, or they could reduce perceived difference depending on whether B is more similar to D than A is to C, and so on. And another criticism of the partial design is that better performance on misaligned than aligned phases may arise due to a bias to respond different when the phases are aligned rather than any change in sensitivity. And the partial design doesn't allow for this measurement of response bias. So as we can see in the partial design here, response bias is a confound because all same trials are incongruent and all different trials are congruent, and that confounds correct responses with congruency. And so this observation prompted the development of the complete composite design here. So in the complete composite phase task, there are two types of changes. So there are congruent changes where the unattended half is the same when the target half is the same, and different when the target half is different, and incongruent changes in which the unattended and target halves have opposing changes. So here the unattended half has changed, but the target half remains the same. That's an incongruent change. And the congruency effect indicates that there was obligatory attention to all the parts, so both halves of the phase, as participants were unable to attend only to the target half, despite explicit instructions to. So the rationale behind this conclusion is that due to holistic processing of the phase, the bottom half of the phase was also processed and then interfered with participants' recognition of the top half. So this congruency effect, it's coupled with a second factor of alignment, such that the test phase can be aligned or misaligned again. And the hallmark of holistic processing here is this two-way interaction between congruency and alignment. So performance measured on sensitivity is better on congruent compared to incongruent trials, and the magnitude of this congruency effect is reduced when parts are misaligned. So overall, it's unclear based on the composite phase task what the results there might indicate in terms of holistic processing. It's possible that they're measuring some other process as well that produces a similar pattern of results, such as a failure of being able to selectively attend to one half, or that they reflect response bias, as might be the case in the partial design. And these findings highlight the importance of having a clear definition of holistic processing. So in the literature, we can find many different definitions of how we might be able to think of holistic processing. And these include things like global face templates, which is the retrieval of whole face exemplars, configural cues, which are emergent cues in whole faces that I'll touch on a little bit later as well, global sampling, where you sample the whole face, and an overland attentional strategy, which is an inability to disengage attention from the whole face. And these are all consistent with certain ideas about how information is processed. For example, this notion that both the top and bottom halves are pulled into a single channel, but they don't make any specific architecture assumptions, and they don't allow us to differentiate between different empirical predictions as well. So to explain how we operationalize holistic processing in our experiments, we must first talk about mental architectures. And mental architectures refer to the organization of mental processes. So both the serial and parallel mental architectures here are multi-channel processing models, meaning that each feature is processed independent of any influence from another feature. So the top half is processed independent of the bottom half. And the difference between these two processing models is the order in which the features in the stimulus are processed. So for serial, you process one followed by the other. And for the parallel model, you process both simultaneously. In contrast to the independent serial and parallel processing architectures, the coactive processing model can be viewed as a form of parallel facilitation model where information from the various stimulus features are kind of pulled into a single channel early on in processing. And so the coactive model only consists of one processing channel instead of multiple independent processing channels. And so provides the most ideal definition of whole object processing. Understanding the stopping rule is also crucial for defining holistic processing. So the serial and parallel models mentioned here can be endowed with either an exhaustive or self-terminating stopping rule. So for example, if participants respond after processing only one of the dimensions, that process is called self-terminating, and in contrast, if they respond after processing both dimensions, then that processing is called exhaustive. So to give an example of the importance of mental architectures and stopping rules, we can consider two separate accounts here for the composite face task results. So according to the parallel model, both halves of a face are represented separately and processed simultaneously, but independently. And this is different from coactive processing, where the halves are pulled into a single representation, so the whole face, which we then process and which informs response. And there are multiple ways that a parallel model might exhibit different processing for upright faces compared to inverted or misaligned faces. For example, a failure to selectively attend to the target half would allow the unattended face half, for example, the bottom half here, to influence processing as well. And with self-termination, this unattended face half might finish first on some trials, and that'll then influence the response as well. So even if the response you receive from both accounts is the same, the processing underlying them are different. So what this serves to show is that an analytic model based on a parallel mental architecture and a self-terminating stopping rule can predict failure of selective attention. And so it's not necessarily holistic processing that is driving that response, and we're unable to differentiate between these accounts based on previous paradigms. So holistic processing can be thought of as a difference in architecture. So where serial and parallel assume independence, but coactivity assumes information pulled together. We could also think of holistic processing with the inclusion of stopping rules that determine the amount of information processed. So for example, where a parallel exhaustive model is more holistic than parallel self-terminating due to processing in both dimensions instead of stopping after one of them. And that allows us to think of a hierarchy of holistic processing, beginning from independent, self-terminating, where you don't have any holism at all, through to coactivity with varying degrees of holistic processing in between. So we need a method to measure both architecture and stopping rule to provide this rigorous means of identifying the holistic versus analytic distinction, as well as possible degrees of holism. And so with SFT and the logical rule models, we can investigate both architecture and stopping rule and can formally define holistic processing as a coactive mental architecture. So before discussing how we can differentiate between the various architectures, I'll first introduce the logical rules framework and the double factorial design. So in this design here, items are split up into two categories that differ on two different dimensions. And for categorization into the target category, the item must both be above the first boundary on the x-axis and above the second boundary on the y-axis. Whereas for categorization into the contrast category, the item must be below the first boundary or below the second boundary. So for example, x1, y0 here is above the boundary on the x-axis, but below the boundary on the y-axis, and so it belongs in the contrast category. And you can see we've also replaced the item values here with specific item labels to make it easier to identify them. So in the target category, we labeled the items low, 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 high, high, low, and high, high to denote low and high discriminability from the contrast category. So for example, this low, low item here is close to both boundaries. And so it has lower discriminability from the contrast category, while the high, high item here is further away from both boundaries, and so has higher discriminability. So with this design, each processing architecture makes qualitatively different predictions for the mean interaction contrast and the survivor interaction contrast. So first we look at the mean interaction contrast, or MIC, predictions here for the target category items. And the MIC is calculated by subtracting the difference in mean RTs on the high-low and high-high items by the difference in mean RTs on the low-low and low-high items. And so for a serial processing model where both dimensions are processed exhaustively, so you process both dimensions, the overall response time predicted is given by the sum of processing both dimensions. So the increase in response time from high-high to high-low should be approximately equal to the increase in response times from low-high to low-low. And so that results in an additive pattern of mean RTs. Whereas for a parallel processing model with exhaustive stopping rule, the overall response time is predicted as the maximum processing time taken to process both dimensions. So the processing time of the high-low, low-high, and high-high, and low-low item will be much closer to each other than to the high-high because they all have one lower discriminability value. And so that results in an under-additive pattern, or an MIC of less than 0. And then for the coactive processing model, because information from both channels is pooled together, it's thought that a single low discriminability value won't slow down the entire response time. But when both dimensions have low discriminability, then processing will be slowed considerably. And so given those predictions, the pattern of response times we see for the coactive model is predicted to be over additive, or an MIC of more than 0. The survivor interaction contrast, or SIC, provides us with further evidence through analysis of the entire response time distribution for each target category item, instead of just the mean RTs like in the MIC. And so as you can see here, the different processing architectures yield different predictions of the form of the SIC function. So both the MIC and SIC have been used to assess the information processing properties of part whole faces. In 2010, FIFIC and Townsend reported finding parallel self-terminating processing for the faces used in their experiments. And their study included 2 conditions. So they had an OR condition and an AND condition, which allowed them to obtain both the MIC and SIC from analyzing the target category items. But neither of them included the full suite of 9 items. So for our current experiments, we are expanding that design in order to also look at contrast category predictions. So with the contrast category items, we can now add further diagnostic predictions seen on the right here. And again, we can see different predictions on the various models, in particular for the coactive model here. We can notice that interior stimuli are processed faster than exterior stimuli. And so what this means is that the closer a contrast category item is to the lower left corner here, so closer to the redundant stimulus, then the faster the predictor response time. And this can seem a little bit counterintuitive because some interior items are closer to the category boundary, and it's also different from what we see in the other models here. But the reason for this is that the step probabilities for the coactive model are determined solely by these bivariate proportions. And so as we approach the lower left, a greater proportion of this item's bivariate distribution will fall in the category B region. And so there's faster evidence accumulation towards the contrast category compared to the exterior stimuli. So moving on to the phases we used in our experiments, we investigated the processing of 2 different types of phases, morphed phases and schematic phases. So the morphed phases were phases that have previously been shown to be best fit by a coactive or parallel self-terminating model. And those phase morphs were shown in whole, but we're presenting our stimuli as composite phases. And in a separate experiment, we also investigated processing of schematic phases, which manipulated lip separation and eye separation in a similar way to FIFIC and Townsend's experiment on the part whole effect. So to begin, we ran the composite phase task, the complete composite phase task, using our composite phase stimuli as shown here on the right. And our task included congruent and incongruent changes for upright and inverted, aligned and misaligned phases. So that allows us to investigate if there are any differences between upright and inverted composite phases as well. And results from that experiment are shown here for both the upright and inverted phase conditions. So we can see this interaction here, which is pretty readily explained. So when the phase halves are aligned, congruent changes are easier than incongruent changes because holistic processing means that you process both halves, which are then changing in the same way with a congruent change. And so in other words, we have two sources of evidence for that response, whereas in contrast, incongruent changes interfere with processing of the attended half, so there's a cost there. And when the phase halves are misaligned, this enhances the ability to ignore the irrelevant half, and so this effective congruency is diminished, which we can see here. And here you can see that the interaction is obtained for both upright and inverted faces, which would implicate holistic processing for both our upright and inverted faces here. In the next part of the experiment, what we did was then we wanted to test a couple of different predictions with the double factorial task. And so in this experiment, we predicted that if only upright faces are processed holistically, then we expect coactivity in the upright aligned condition. And if it's alignment that affects our processing of the composite phase stimuli as faces, then we expect to find coactivity with the aligned faces and serial or parallel processing with the misaligned faces. And if composite faces are processed as separable objects altogether, then we expect serial or parallel processing in all four conditions. So these are the morphed faces used in our experiment in the double factorial design. So we begin with 4 base halves here, which we then morphed to form a third, and then we combined these to form this 9-item stimulus space here. So the task was a categorization task, and participants were shown a fixation cross presented with a face and asked to make a categorization response, followed by an interstimulus interval, another fixation cross, next stimulus, and they got feedback presented if the categorization response was incorrect. So here are the results from the SFT task, and there's a lot of information contained in these plots. I put in the predictions here for each of the models on the side, but I think there's just a lot on these slides. So I just wanted to quickly summarize the main take-home messages. First is that there's very little evidence of coactivity in the upright aligned condition, which is on this slide that we can see here. And second, with regards to architecture and stopping rule, there's actually a lot of similarity between the results from all 4 of our phase conditions. And that was that we mainly see evidence for serial and parallel processing and no strong evidence for coactivity. So I'll just run through these slides here that show all the results. But yeah. So if we had time to actually go through all of these slides, what we would see from our MIC and SIC results is generally mixed results across the conditions and little evidence of coactivity. So we decided to also fit models to this data and do some model comparison analysis, which allows us to summarize the results efficiently and also allows us to consider both correct and error performance across all of the items at once. And that's different from the SFT analyses I just showed, which are restricted to subsets of items. So for example, the MIC and SIC, we can only get with the target category items. So besides the serial and parallel self-terminating models, we also fit a mixed serial parallel model, which has a parameter indicating a mixture of serial and parallel trials. We also fit contaminant serial and parallel models. So these models assume that most of the trials are generated by the main model. So for the serial one, that would be the serial model. And in these models, some trials are generated by a contaminant process where response times from this process, they're drawn from a uniform component that kind of spans the range of response times actually observed. So for the contaminant zero model, it's a mixture of the zero model and a uniform model that accounts for randomness. And then lastly, we also fit the coactive model and an additional model called the free drift rate model, which can essentially be considered a very flexible coactive model. So unlike the zero and parallel models that have separate pairs of accumulators for the 2 dimensions and drift rates that are derived from the marginal distributions, the coactive model has only one set for the whole phase here, and the drift rate is derived from a bivariate normal distribution. So for the coactive model, we assume that each stimulus location is identified by a bivariate normal distribution of perceptual effects, and that these perceptual effects along the 2 dimensions, so the top and bottom phase halves, are statistically independent for each stimulus. So the mean locations of the items were determined using multidimensional scaling, and the MDS solutions we obtained here suggested that we could constrain the faces to a grid in each condition. And this suggests something about the separability of the faces, given we can constrain them to a grid, which is not quite what you would expect from holistic processing. And by constraining to a grid like this as well, we assume fixed decision bounds and fixed mean locations. So again, to provide a more powerful test of coactivity that is unconstrained by our assumptions of the locations or variances of each stimulus, we fit a free drift rate model here, which simply estimates as a free parameter the drift rate associated with each stimulus to provide a very kind of flexible comparison. So it allows for unconstrained mean location and variance. And we fit the models to each individual using DMCMC with informative price over parameters and compared the models using DIC from the posterior model fits. Okay. So to summarize the results, on this slide here, I've highlighted the best fitting model. And what we can see is that the coactive model was not preferred for any participant. The free drift rate model was preferred for 2 participants, and this was in the 2 aligned conditions. And the mixed zero parallel model here was preferred for most participants. The best fitting model is also fitting well at the level of individual item conditions. So I've got a subset shown here for the upright aligned condition. Okay, so to further investigate the idea of holistic phase processing, we ran a second experiment where we manipulated second-degree configural information, similar to FIFIC and TOWNSEND'S part-hole experiment. So these are the phases here. And this spacing between the various features in the phase has also been suggested to be an important cue we use when processing phases. So for the morphed phases in the first experiment, we would also have some ambiguity around what values the top and bottom phase halves are, and where they lie in the stimulus space that we show depends on someone's perception of the similarity between the phases. But for the schematic phases here, we have fixed values that represent the differences between the space between eyes and lip height. And so we can look at potential changes in architecture when these 2 second-order relational facial features are manipulated. So for these schematic phases, again, we ran the composite phase task with them, and we only obtained the interaction for upright phases here, which would implicate holistic processing for upright schematic phases, but not inverted schematic phases in the composite phase task. Similarly, we wanted to test a couple of different predictions. I'll quickly summarize that. if upright faces are processed holistically, we expect coactivity for upright aligned. If it's alignment, then we expect coactivity with aligned, zero parallel with misaligned. And if they're separable objects, we expect zero parallel in all 4 conditions. And so in this experiment, to create the 9-item stimulus space, we combined small, medium, and large spaces between eyes and lip height as shown here. So again, I have 4 slides of a lot of information. And in this one here, in the upright align condition, what we can see is just one participant showing the hallmark signatures of coactivity. But similar patterns of zero and parallel processing are found in the rest of the participants and also across the other conditions as well, as I'll show here. So before fitting our models again, we obtained MDS solutions for our schematic phase stimuli as well. And here we can see that for the upright conditions, the solutions are constrained Euclidean, where we can set R equals 2. And for our inverted phase conditions, we found R greater than 2, suggesting more of a dominance of one dimension over the other. So that similarity between the faces is being dominated by the larger difference. For example, that similarity between the faces is dominated by the difference between IX and EX, more in the inverted misaligned compared to the upright misaligned condition. So we fit the same 7 models, and again, highlighted is the best fitting model. And we can see the coactive model is not preferred for any participant. The free drift rate model was preferred for 3 participants. Mixed serial contaminant model is preferred for 2. That basically indicates consistency with serial processing. And the mixed serial parallel model was preferred for most participants here. And again, I just wanted to present a subset of the best fitting model fits, and you can see that they fit pretty well. So some interim conclusions here were that most participants were best fit by the mixed zero parallel model, and we had little evidence of coactivity. This mixture model that we're talking about here has provided good fits for several other stimulus types as well, such as overlapped separable dimensions and whole object features, such as size and color varied within a single object. And so overall, this suggests that most participants treated the composite faces like other objects with separable dimensions instead of as whole integral objects in this task. And so our results suggest that composite phases are not necessarily processed holistically, at least in terms of coactivity. And instead, this interaction in the composite phase task could be due to an inability to selectively attend to just the target half, and so culminates in interference from the non-target half. So there seem to be 2 questions that arise from our results here. The first is, why do we observe hallmark signatures of holistic processing for upright faces in the composite phase task, but not in the SFT task? And the second is whether processing is really a mixture of serial and parallel processing. So to address the first question, a potential explanation of these results is related to work carried out by Lynch et al., which combined the complete composite phase task with a signal to respond paradigm. So that manipulates the amount of time to make a face recognition decision. And so in this study, for example, you've got a fixation cross here, followed by a study phase, blank screen, and then a test phase. And this response signal is shown with X's, and they appeared at one of 6 time lags from 50 to 1800 milliseconds. And so this is a complete composite phase task. And in the top row here, what you can see is an example of an incongruent change in the aligned condition, where the top half is the same and the bottom half has changed. So in the study, resulting changes in accuracy were then mapped over the time course of processing. And what they found was that holistic processing, in terms of this interaction effect, emerges late in the time course. So it emerged at around 400 milliseconds for easy to discriminate faces, and more than 1,000 milliseconds for difficult to discriminate faces. And so it suggests that as discriminations get harder, this interaction between alignment and congruency takes longer to arise. And so participants might be responding before holistic processing comes about. And so perhaps that's one thing that's happening in our studies, is that SFT task discriminations are very difficult to make, resulting in holistic processing only emerging later on in the time course of processing. For the second question about whether or not processing is really a mixture of serial and parallel processing, we ran a third experiment. So from results from the early experiments, we can see instances of mixed results where SICs might show evidence of serial processing, while MICs then show evidence of parallel processing, or vice versa. And the mixed serial parallel model also fit most participants' data best according to model comparisons. So that's from our previous experiments. This idea of a mixture of processing architectures has been discussed in previous simulation studies as well. So in this figure here from Little et al., we can see that varying the mixture proportion results in diagnostic contrast to vary smoothly from one component's predictions to another. So for example, SIC transitions smoothly between the parallel predictions to a serial prediction here. However, this similar systematic transition in SIC functions as model parameters change was also observed by Idles et al. When they investigated interactive parallel models. And an example here is of the inhibitory parallel model, where processing occurs in parallel but with inhibitory cross-channel interaction. And the inhibitory SIC predictions resemble the parallel serial model predictions for the exhaustive models here, where we can see the transition from parallel to serial. So SFT cannot differentiate a mixture model from an interactive parallel model, and so we need an alternative method for differentiating these explanations, which brings us to the next experiment on fixed point analyses. So according to fixed point analyses, mixture distributions demonstrate what is called a fixed point property. And so here in panel A, what we can see is density plots for two base distributions. The blue one reflects a response time distribution for D1, red for D2. And in panel B, what we see is three mixtures of these two base distributions with the mixture proportions here. And this vertical line in both panels indicates the fixed point. And importantly, mixture models are the only ones that predict a fixed point. And if you mix two distributions in different proportions, the resulting mixtures will always cross over at a single point. Yes, we all know response time distributions are noisy distributions, and we can't really measure response times perfectly. And a histogram estimator depends on the chosen bandwidth, which might affect the location of the crossover points. So we analyze our results by first fitting an X-Gaussian distribution to the response times, because they're good at producing response time distributions or positively skewed distributions, and assumed priors over the mean, SD, and tau parameters that tell us about shape of the tail. So the X-Gaussian fit the RT distributions very well. And the figure shows an example of the posterior predictive fits of the X-Gaussian distribution to one of the participants. So that allows us to better estimate the crossover points. And because we used posterior estimation to evaluate the fixed point, what we end up with is a distribution of possible crossover locations. And so as we can see in these figures, in this simulation from an inhibitory parallel model, there's not a single crossover fixed point. And in this right figure here, this shows the distributions where they cross zero. So if it were a single fixed point, the distributions would be in the same place. So for this one, the zero crossing is probably in 3 different locations. And this is in comparison to the results we found when we simulated a mixed seroparallel model with selective influence. Selective influence here refers to how the separation between the phase halves is the only thing affecting the mixture parameter. And so on the right here, what we can see is large evidence. We have a mixture model compared to the inhibitory parallel simulation here. So in further comparisons, we can see that breaking selective influence or changing other parameters besides the mixture parameter can break this fixed point property. So as we can see in the 2 examples on the left here compared to the one on the right, there are distinct separations, making it unlikely we find 1 zero crossing point compared to this one here. And so what this shows is that finding the fixed point property is actually very hard. So number one, response time data are noisy. So you need a way to estimate the fixed point. Number two, finding the fixed point requires that only the mixture proportion is changing across stimulus conditions, not other parameters. And you need to have consistently varying response times as well across at least 3 conditions. And all of these requirements are difficult to meet. So when you do find it, that's an extremely strong indicator of a mixture model. And we can assume that the only thing separating the phases effects is this mixture of zero and parallel processing. If we don't find the fixed point property, then we're unable to rule out any of these models. So we wanted to determine whether we can observe this fixed point property using stimuli, which have previously been explained with the mixture model, so our stimuli. And in this experiment, we manipulated spatial distance, as our prior results indicated this had an effect on the relative proportion of zero processing. So the task involved identification of 4 stimuli, each with an individual response. And 2 values were crossed on each dimension, so exhaustive processing was necessary for the response. So these 4 stimuli here are derived from the target category in the original design. And we had 6 participants complete all 3 separation levels from 0 to 350 pixels with different counterbalance orders for each participant. There was an identification task with testing over 4 sessions, and participants had to learn to identify the 4 phases while this horizontal shift between the 2 halves could vary. So they were shown a fixation cross, the stimulus, make a response, and then show the next stimulus and so on. So results-wise, 3 of the participants didn't show a strong differentiation between 0 and 100 pixel separation. So that manipulation didn't work as strongly as expected. One of the participants had multimodal zero crossing densities, and the 350 pixel separation didn't slow down performance as expected. So they were likely adjusting other parameters as well, like their thresholds. And 2 of the participants showed evidence for this strong fixed point prediction. And because it's so difficult to find the fixed point property, we have pretty good evidence of the mixture model here. So to summarize this experiment, previous simulations have shown that interactive parallel models can mimic mixture models, such as the one that we found best fit most of our participants. And so it was unclear whether our results showed a true mixture model. But with the fixed point property, we were able to find independent evidence for the strong fixed point prediction in categorization response times for our phase stimuli. I've got a 5-minute warning, sorry. Overall conclusions for overall is that there was very little evidence of coactivity for both morphed and schematic composite phases, and these were best fit by a mixture of serial and parallel processing. And we also got good evidence of a fixed point independently, which indicates a mixture model. So what this suggests is that holistic processing could be a misnomer, or holistic processing actually implies something different. So perhaps harking back to that hierarchy of holism, perhaps parallel processing is indicative of weak holism. Something else that could be at play as well is perhaps this time course of holistic processing, where discriminability of our phase stimuli within our categorization task could be too difficult. But overall, our results are more in line with the notion of an overland attentional strategy. And perhaps coactivity versus independent processing might be linked to how easily attention can be allocated to different dimensions. And that's all. Thank you. Sorry, that was I think I've gone over time, but thank you, everyone.
I turned the mic on so you could hear the rowdy applause in the room. We have time for maybe one question. Andy, did you?
Sure, thanks. That was super interesting and heroic. I have, sorry if this is a naive question, but I kept wondering, the mixed serial parallel model, is that saying that some people on some trials are using serial processing and sometimes parallel processing, or is it saying on the same trial they might flip back and forth? And or can you tell the difference between those? Yeah.
That one is about some trials being serial and some trials being parallel. We haven't looked into whether they're flipping between processing on a single trial. And so in terms of, I don't think in terms of our model comparisons that we're able to tell the difference there, but there's one parameter in the mixture model which just indicates the number of parallel trials, for example, in a serial model and so on.
We might have time for another question.
Oh.
Oh yeah, Kevin, you had a question. Did you want to chime in?
Hey, Jun, really interesting talk. Really cool. I was just wondering if do your results then maybe suggest the features, the lower level features, facial features are essentially getting bound together upstream later? That's why maybe you're seeing the later, the interaction later on in processing. So maybe it's like kind of like in a similar sense as the feature integration theory. So would you say that's consistent with your results?
I'm not very sure about that. So I think in our experiments, what we can see here is that holistic processing, or at least in our experiments, is at this level of representation. And this relationship between how faces are perceived and represented might not quite be the same as what's measured by the decision architectures. Maybe the representation is holistic, but then selective attention then acts on that representation in a way that breaks down holistic representation. Yeah, I'm
cool. Very interesting. Cool.
Yeah.
Great job.
Thank you.
Hey, Juno, it's Paul.
Hi.
So one of the things I was thinking about is faces have emotional correlations, right? Like smiling eyes is a thing. So do you think the general perception that, you know, most people, if you explain holistic facial processing, they get it intuitively? Like yeah, I understand how you just kind of see a face and you get it. Could that come from something like the emotional aspects of like highly correlated features? And what we have in these studies are kind of like blank emotionless faces, and therefore there's none of that kind of additional information that we would normally use to get a gestalt understanding of what a face is doing and how similar it is.
I think potentially, but I believe there've also been more recent studies where they've also looked at kind of the emotional information in slightly different paradigms as well. And I think the evidence behind that at the moment is also still unclear in terms of whether or not we do see holistic processing kind of in terms of the gestalt of the whole face. So I'm not very sure. It's an
Perfect answer.
interesting thought to think about.
All right, if there aren't any other questions, we might call it there. Thanks, Jen, for your talk. Thanks everyone for attending.
Thank you, everyone.